All right, so now we're going to talk about our first set of alpha carbon reactions, which is alpha carbon halogenation. So this is obviously just sticking a halogen on that alpha carbon. Okay, this is actually, we're going to see that this can occur under acidic and basic conditions. There's going to be a little bit of a catch between the two of them, but nonetheless. So here we start out with our ketone. We're going to, this first one we're going to cover is under acidic conditions. And of course, notice that we're just going to have substitution on that alpha carbon, right? So there used to be one of those acidic hydrogens here. Now there's this halogen bromine. This, you can do it with chlorine, bromine, or iodine. Like usual, fluorine is left out of the bunch. So under acidic conditions, again, what we're gonna, the reactive species in all of these reactions is either gonna be the enol or the enolate, okay? Under acidic conditions, it's going to be the enol, and under basic conditions, it's going to be the enolate. But let's go ahead and remember that we can do the reaction mechanism for the enol formation under acidic conditions. What's the first step? Protonation of that carbonyl oxygen. This creates our enol, almost. This creates, through resonance, we can get protonation, I'm sorry, not protonation. We can get our positive charge moved down to that carbon, and now water can accept that acidic hydrogen, forming our enol, okay? So the enol is really the reactive species in this reaction. And again, we saw through resonance that the enol has a relatively nucleophilic alpha carbon. And so that's exactly what's going to happen here. We're going to see that pair of electrons in that pi bond play the role of the nucleophile attacking that bromine. Specifically though, notice how the bromine goes on the alpha carbon. It does not go on the carbonyl carbon, or what will be the carbonyl carbon. Whoops. And at the same time, this pair of electrons will come down. Now we can just go ahead and deprotonate that carbonyl oxygen, leaving us with a brominated alpha carbon. Okay, so notice how first step is formation of the enol, and then the enol is going to be the species that reacts with bromine. This is going, if you have any sort of like any sort of an asymmetric ketone, the bromine is going to tend to want to go onto the more highly substituted carbon, right? So this is the major product where bromine has joined onto the more highly substituted carbon, not this other alpha carbon, which is less highly substituted. Okay, and the reason for that is because, remember, the first step in this reaction is the formation of the enol. Well, the more highly substituted carbon will form, oops, let's just be consistent with color. The more highly substituted carbon will form the more stable enol, right? Because remember, when we're talking about alkenes, the more highly substituted is the more stable alkene. Right? So in this case, it will form the more stable enol, and so that will be the species that reacts with bromine. Okay. Yeah, okay, so then if we, let's say that we do that, what this one is saying is basically we can then follow that up by treatment with a base and get an elimination reaction, right? So in the first step, I have no room to draw here, so give me a second. So in this first step here, I have formation, or rather halogenation, bromination of the alpha carbon. That's what this first step does. And then in my second step, I can treat that with base and get an elimination reaction, an E2, or I guess in this case, actually, it could be an E1. You know, another favorite base that we like to use could be tert butoxide. Really any sort of a strong base treating this would give us our elimination afterwards. Okay, so now under basic conditions, let's go ahead and do this mechanism here. Notice, and this is going to be an important thing, This carbon here does not have any alpha hydrogens. So there is no chance of us brominating that particular carbon because the first step in all of these is enol or enolate formation, always going to require that acidic alpha hydrogen. So just in this particular example, this red carbon has no alpha hydrogens, so you're not going to be able to have substitution on that carbon. So now we're looking at just this one here. So let's go through the mechanism. Here we have, again, this whole shtick of this chapter is that that alpha hydrogen is relatively acidic, it can be removed. And then our enolate ion will act as a nucleophile attacking bromine. Okay? So this is, again, sort of the same reaction, but occurring under basic conditions. The catch, and the big difference as far as we're concerned, is that under basic conditions, you will get polyhalogenation, meaning that every single alpha carbon, and let's just write this down to be clear, every alpha hydrogen will be replaced by the halogen. So in this case, I had two alpha hydrogens. Both of them are going to be replaced under basic conditions, okay? You can't stop it just at the one step. The reason is that after you get that first step, right? After I get my first step, this hydrogen here is even easier to remove, okay? It's even more acidic than what we started out with. And then just to like hammer this home, let's say that these weren't two methyl groups, but instead these were also two hydrogens, then they would also be brominated. Okay, so again, every alpha hydrogen will be replaced by a halogen under basic conditions. Another reaction that we're going to cover, which is similar but kind of has its own little special class, is called the Held-Bullard-Zelinki. Those must be the three chemists who discovered it. But this is a way to brominate the alpha carbon of a carboxylic acid. Okay, the problem with a carboxylic acids relative to our other carboxylic acid derivatives is, yes, you have these alpha hydrogens, and yes, they're relatively acidic, but you have this other carboxylic acid hydrogen, which is way more acidic. So any base that you treat this compound with, it will immediately protonate this site, rather deprotonate this site and not your alpha hydrogens, okay? So if we want bromination of our alpha carbon, basically have to use, do something a little bit trickier, which is to use this combination of reagents. So what does PBr do to our carboxylic acid? This actually probably should have been covered last chapter, but it wasn't. Remember, what does PBr do to alcohols? This is something we learned back last semester. You get substitution of the hydroxide group for a halogen. So it does the exact same thing here, forming an acyl bromide, an acid halide. I like calling them acyl halides, but whatever. But yeah, you get an acyl bromide that's formed. So I'm not sure why this wasn't in last chapter. We learned about SOCl2, which is a way to form an acyl chloride, but we kind of should have learned about this one too. But anyway, so the first step is basically you got to get rid of that hydroxide group, got to get rid of that acidic proton. Now, this structure here is going to be tautomerize to form an, it's called acid halide enol. Basically, right, we have this is just our normal ketone enol tautomerization. Then we can treat this with bromine. We know that enols react with bromine at that alpha carbon. And now we have an acyl halide with this alpha carbon brominated. And what happens when we add water to our acyl bromide? Remember that we just get conversion back to a carboxylic acid. This is one of the reactions we learned last chapter. Acyl halides will react with water to form carboxylic acids. Okay, so this is the HVZ reaction, just kind of a special case where we're brominating the alpha carbon of a carboxylic acid. Okay, another reaction that's sort of lumped into this chapter is what's called the haloform reaction. Here we're treating with sodium hydroxide and then bromine, and then following that up with acid. And notice that that's actually replacing a methyl group with a carboxylic acid group. So this is a way to convert methyl ketones into carboxylic acids. So how does that work? Well, I guess the first step, since they're going to skip it, is one that we just learned about here. So step one is you're going to have sodium hydroxide and bromine. What's that going to do? Remember that under basic conditions, every alpha hydrogen you have will be replaced with bromine. And so that's exactly what we're going to see here, is that every single one of these alpha hydrogens, again, note this carbon here didn't have any alpha hydrogens, so we didn't have to worry about that, is going to be replaced with bromine, right? So then the next step, so then this is what happens after that, is once you have all of those hydrogens replaced with bromines, now you're going to have your hydroxide ion acting as a nucleophile, attacking that carbonyl carbon. This is going to give us our tetrahedral intermediate, right? And what did I hopefully drill into your brain about tetrahedral intermediates? What do we ask ourselves when a tetrahedral intermediate forms? Do I have a good leaving group? And surprisingly, this guy right here is a good leaving group. Okay, so this is something new that we're learning about here, but that's exactly what happens next, is your tetrahedral intermediate will collapse and kick off that good leaving group, leaving you with a carboxylic acid. The last step will be, this guy here is a good base, right? So this guy can go and attack that hydrogen. Oh, I guess that's right below. So the last step there is deprotonating that carboxylic acid. So this is how you get this carboxylate ion. Again, you sort of convert that methyl group into this great leaving group, the CBr3, and then, yeah, that gets kicked off. Okay, this is something, these haloform reactions are something that you see when your other alpha carbon doesn't have any other alpha protons, right? So any other alpha hydrogens. Otherwise, every single site will get brominated, and it just sort of doesn't work as well. So if you're really going for converting a methyl ketone to a carboxylic acid, this R group here, this R alpha carbon can't have any hydrogens. Okay, so just a summary of the reactions. We learned both under acidic, this would be under acidic conditions. We have bromination of the alpha carbon. Remember, under basic conditions, we have the same thing, except for we get polyhalogenation. And then we learned about these two special reactions, the HVZ and the haloform reactions. And as is going to be the case for, I think, everything in this chapter, at least safe to say almost everything in this chapter, we should know mechanisms for all three of these. Okay, mechanisms are going to be another very important part of this chapter.